Welcome to another unit in the workbook Statistics. This time I'm going to talk about stochastic inequalities and in particular about the two mainly important inequalities, which are the Markov and the Chebyshev inequality. Well, let's have a look at the Markov inequality first. Here we can get something like an upper bound on the probability that our random variable x is larger or equal to a value a. And this upper bound is given as the average, the mean, divided by this value a. The really interesting thing about this Markov inequality is that this holds independent of the distribution being assumed. So we do not need any kind of normal distribution, whatever underlying our data set. We just can work with this upper bound, with this estimate on our probability, independent of any kind of probability. Well, how do we get this Markov inequality? Well, we can simply start with the definition of the mean. That's more or less for a continuous distribution, the definition of the mean. Well, that's the integral from 0 to infinity. So we could split this integral up into one part going from 0 to a and a second part going from a to infinity. That's more or less simply the same as splitting up a sum into two parts, because they again connect. Up to this, it's still exactly equal to the mean. Now, well, whatever we get here will be positive. So if we leave this part out, if we only take that part, we will have something which is smaller than the sum of both of them, or equal to. So that's where we get the larger or equal to this one. We simply leave this expression. So we have this part here. Then, well, we can replace x with our parameter a, with the assumption that x will always be slightly larger than the a, which makes sense because, well, x starts at a, goes to infinity, so x automatically is always larger than a or equal to. That's why this expression with an x between a and infinity will be larger or equal to the same expression where we fix the a to the lower bound. Well, now this is no longer a variable. This is a parameter, fixed parameter, which we can pull in front of our integral. It looks like this. This integral, however, is nothing else than the probability that x will be larger than this a. So what we get is actually this inequality. This part on the left, then the larger equal to parts, then this part on the right. And well, if you look closely, you see that we only have to divide by a to get our Markov inequality. So it's actually pretty straightforward getting this inequality. However, well, it's easy, it's straightforward, it doesn't really have any kind of requirements. That's why it's also pretty inaccurate. Therefore, if we know a little bit more, we are switching from Markov to Chebyshev, and that's the next slide, which is a bit more exact. As I said, we're talking about the Chebyshev inequality next. And the Chebyshev inequality, well, I said it's a bit more precise than the Markov inequality, but it also focuses on a slightly different probability. Here we want to know that the distance of our random variable from the mean is larger than a value a. And this probability can be estimated to be smaller than the variance divided by the parameter a squared. So here we talk about a deviation from the mean, whereas with the Markov inequality we're talking about the probability of a random variable being larger than value a. Well, how can we get to this Chebyshev inequality? I'm just going to sketch the proof here. In general, we could simply take the Markov inequality. Instead of using a random variable x there, we're going to replace this x, this random variable from Markov, with a random variable y minus the mean of y, and then parentheses squared. And we're replacing also the a from Markov with a b squared. So we'll look like this. That's just x being larger or equal to a from Markov, but with these two special versions. Then we have mean divided by a with Markov. Well, that's the mean of this variable, the expected value. Divided by a, well, a is b squared here. If we look closely, this part here is similar to a variance of y. Also, this part here could be estimated in the following fashion. So we would get this result. This result is more or less exactly the same to what we have up here. The only difference being this is called A and this is called B. But in the end, it's just a slightly different version of the Markov inequality. However, with a different focus in mind. And well, that's already everything I wanted to mention regarding Markov and Chebyshev inequalities. Hope you enjoyed this short session. I say goodbye and see you next time.